Around 2.5 billion years ago, oxygen was basically toxic waste. There were no animals breathing it, no trees producing it, and absolutely nobody taking a deep breath and saying, "Ah, fresh air." In fact, breathing the atmosphere back then would kill you almost immediately, although to be fair, so would almost everything else about the planet. The oceans were full of microscopic organisms that had spent billions of years evolving without oxygen. They did not need it. They did not want it, and many of them were chemically incapable of surviving around it. Then a group of tiny microbes appeared and began pumping oxygen into the world, like a factory dumping waste into a river. At first, nothing dramatic happened because Earth kept absorbing it, but the microbes did not stop. They kept multiplying, kept photosynthesizing, and kept releasing more oxygen until the oceans began rusting. The atmosphere changed, the planet may have partially frozen, and huge parts of the existing biosphere were forced to escape, adapt, or die. This was the Great Oxidation Event, possibly the first time life nearly ruined the planet by being too successful. To understand how strange this was, you have to forget almost everything you know about Earth. Go back more than 3 billion years. There are no forests, no grass, no fish, no insects, no footprints, and no birds screaming outside your window at 5 in the morning. Most life is microscopic and lives in the oceans, mud, rocks, and volcanic environments. The atmosphere contains almost no free oxygen. Instead, many organisms survive using chemical reactions that would sound completely alien today. Some consume hydrogen, some use sulfur, others produce methane. To them, an oxygen-free planet is not some horrible wasteland. It is perfect. Oxygen would have been the problem. Photosynthesis already existed, but early versions did not always release oxygen. Some microbes use sunlight and chemicals such as hydrogen sulfide. This worked, but hydrogen sulfide is not available everywhere. Then the ancestors of Cyanobacteria discovered a ridiculous biological cheat code. They learned how to use water. Water covered most of the planet, so suddenly these microbes had access to an enormous supply of the ingredients they needed. Using sunlight, they split water molecules, built food for themselves, and threw away the leftover oxygen. That last part was important because oxygen is not a gentle substance. It is highly reactive. It damages proteins, attacks cell membranes, interferes with enzymes, and helps create aggressive molecules called reactive oxygen species. These molecules behave like tiny chemical vandals. They break things, steal electrons, damage DNA, and generally make a cell regret being alive. Your body survives oxygen because billions of years of evolution have given your cells antioxidants, repair systems, and special enzymes that keep the damage under control. Early organisms did not necessarily have any of that. Their cells had been designed for a world where oxygen was barely present. Exposing them to it would be like dropping a deep-sea fish into a swimming pool filled with bleach and then asking why it looks unhappy. So, cyanobacteria were not simply producing fresh air for future animals. They were producing pollution. Every day, giant microbial mats sat in shallow water, absorbed sunlight, and released oxygen into their surroundings. But for a long time, Earth had a solution. It simply ate the oxygen. The ancient oceans contained enormous amounts of dissolved iron. When oxygen met that iron, the two reacted and formed iron oxides. In other words, rust. The rust particles sank to the seafloor and accumulated in enormous layers. Today, these rocks are called banded iron formations, and they look like striped slabs of red, black, and gray stone. A huge amount of the iron humans mine today exists because microscopic organisms caused the ocean to rust billions of years ago. So technically, cyanobacteria were running the planet's first mining operation, although their employee benefits were terrible. Iron was not the only thing removing oxygen. Volcanic gases reacted with it. Minerals in the crust absorbed it. Dead organic material consumed it as it decayed. Cyanobacteria kept producing oxygen, and Earth kept making it disappear. Around the microbial mats, small pockets of oxygen-rich water may have formed during the day, only to shrink again later. For organisms adapted to oxygen-free conditions, these areas would have been dangerous chemical zones. But most of the planet remained safe for them. Oxygen existed, but it could not yet take over. This may have continued for hundreds of millions of years. Cyanobacteria had invented oxygen-producing photosynthesis, but the atmosphere refused to keep the oxygen. Imagine repeatedly filling a bathtub while someone has drilled 10,000 holes in the bottom. You can keep pouring, but the water level is not moving. Eventually, though, enough of Earth's iron, minerals, and gases had reacted with oxygen that the planet could no longer remove it as quickly as cyanobacteria produced it. The holes were filling. Somewhere around 2.4 billion years ago, oxygen began accumulating more permanently in the atmosphere. This was when the old world started losing control. Scientists know something enormous changed because the rocks suddenly began behaving differently. In older rocks, they find minerals that can only survive when oxygen is absent. Later, those minerals disappear from river sediments because oxygen destroys them before they can be deposited. At the same time, red-colored rocks stained by oxidized iron become more common. Even sulfur atoms preserve evidence of the atmospheric change. Before oxygen accumulated, sunlight created unusual sulfur patterns that could form only beneath an oxygen-poor atmosphere. Afterward, those patterns mostly vanished. Earth did not leave behind a written diary, but it did leave behind several billion years of extremely rusty receipts. The Great Oxidation Event was not one sudden morning when the entire sky filled with oxygen. Nobody went to sleep in an oxygen-free world and woke up next to a tree. The change occurred through pulses, reversals, and long periods that scientists are still trying to reconstruct. Oxygen levels may have risen, fallen, and risen again. But even a small permanent increase would have been devastating for organisms that could not tolerate it. Oxygen spread through surface waters and attacked the chemistry that many microbes relied on. Enzymes stopped functioning. Cellular components became damaged. Environments that had been safe for countless generations became hostile. The organisms living there faced three options. They could evolve defenses, move into oxygen-free refuges, or become microscopic history. Exactly how many organisms died is impossible to know. These were tiny cells living more than 2 billion years ago, and microorganisms are not especially considerate when it comes to leaving complete fossil records. We cannot line up their skeletons, count the species, and call it a mass extinction with the same confidence we can for dinosaurs or trilobites. But oxygen-sensitive life almost certainly lost enormous areas of habitat. Entire microbial communities may have disappeared from shallow oceans and exposed sediments. The survivors retreated into mud, deep water, underground environments, and other places where oxygen could not reach. Their descendants are still here. Anaerobic microbes live in swamps, seafloor sediments, animal intestines, stagnant ponds, and deep underground. Some are so sensitive that oxygen kills them. They are not primitive failures waiting to evolve into something better. They are survivors from an older version of Earth, still following rules that existed before the atmosphere changed. Even after oxygen began accumulating, most of the ocean did not suddenly become clean, blue, and full of dolphins. Surface waters might contain oxygen, while the deeper ocean remained oxygen-free. Some deeper waters may also have contained large amounts of hydrogen sulfide, the gas that smells like rotten eggs and becomes toxic at high concentrations. This created a planet with different layers of danger. Near the surface, oxygen-threatened organisms adapted to the old world. Deeper down, sulfide and a lack of oxygen threatened organisms trying to use the new chemistry. There was no universally safe zone. The ocean had basically divided itself into several hostile departments, each with a different way to kill you. Then oxygen may have helped create an even bigger problem. Before oxygen rose, methane produced by microorganisms probably helped keep Earth warm. The sun was dimmer than it is today, and methane is a powerful greenhouse gas. It acted like part of the planet's thermal blanket, but oxygen reacts with methane and helps remove it from the atmosphere. As oxygen increased, methane may have decreased. The blanket became thinner. Around the same broad period, Earth entered a series of severe ice ages known as the Huronian glaciations. Ice may have spread incredibly far, possibly reaching low latitudes. Scientists still debate exactly how strongly the rise of oxygen caused this cooling, so we cannot blame cyanobacteria for the entire thing with complete confidence. But the timing suggests that oxygen's destruction of methane may have helped push the planet toward a deep freeze. So these microscopic organisms may have polluted the oceans, attacked other life, changed the atmosphere, and helped freeze much of Earth, all while sitting in shallow water doing photosynthesis. That is an impressive amount of damage for something without a brain. The cyanobacteria were not evil, of course. They were not planning a hostile takeover. They had simply discovered an extremely successful way to obtain energy, and evolution rewarded them for doing more of it. But their success changed the entire planet. This may have been the earliest example of life transforming its own environment so dramatically that it created a crisis for nearly everyone, including itself. Eventually, some organisms developed ways to defend themselves against oxygen. They evolved enzymes that neutralize dangerous oxygen compounds. They improved cellular repair systems. Then life discovered that oxygen's dangerous reactivity could also be incredibly useful. If controlled carefully, oxygen allows cells to extract far more usable energy from food than many oxygen-free processes. It was still poison, but now was poison connected to an extremely powerful engine. Life had essentially found a tiger, built a cage around it, and started using it to generate electricity. This did not immediately create animals or complex life. Oxygen levels remained much lower than today's for an enormous amount of time. The first large animals were still more than 1 billion years away. But the basic rules had changed forever. Organisms that could use oxygen gained access to a new and powerful source of energy. Organisms that could not tolerate it were pushed farther into the remaining oxygen-free corners of the planet. Oxygen also began producing ozone high in the atmosphere. Ozone forms when ultraviolet radiation interacts with oxygen molecules, and although ozone near the ground can be harmful, the ozone layer high above Earth absorbs much of the sun's damaging ultraviolet radiation. This meant oxygen was doing two completely opposite things at once. Near living cells, it could damage proteins and DNA. High in the atmosphere, it helped protect life from radiation that damages proteins and DNA. Oxygen had become both the poison and the sunscreen. Over the following billions of years, more organisms learned to use it. Complex cells evolved. Multicellular life appeared. Animals eventually developed bodies that depended on oxygen being delivered through blood, gills, lungs, and circulatory systems. Much later, humans appeared and began treating oxygen as the most natural and harmless thing imaginable. But oxygen never actually became harmless. Your cells produce dangerous oxygen compounds every second simply by staying alive. Your body constantly repairs damage caused partly by the same gas it requires for energy. Breathing oxygen at unusually high pressures or concentrations can damage the lungs, nervous system, and other tissues. Fire also depends on oxygen, meaning the gas that powers complex life can help erase an entire forest in hours. We do not survive because oxygen stopped being toxic. We survive because life spent billions of years learning how to use it without immediately falling apart. That is what makes the Great Oxidation Event so strange. There was no asteroid, no giant predator, no supervolcano suddenly covering the world in lava. The threat came from microscopic organisms releasing their waste. That waste rusted the oceans, transformed the atmosphere, threatened much of the life already on Earth, and may have helped freeze the planet. But it also created the conditions that eventually allowed complex life to exist. Every animal, every forest, every dinosaur, and every human being came from a world rebuilt around what was once pollution. So every time you take a breath, you are inhaling the leftovers of an ancient environmental disaster. Oxygen did not begin as the gas of life. It began as toxic waste, and life had to evolve fast enough to survive its own invention.